Imagine standing over an entirely empty landscape. To build a functioning city, the first thing we need is a map. In mathematics, we use straight lines to lay down our very first precise roads across this blank grid. The simplest road you can build is one that runs perfectly straight up and down, north to south. It crosses the horizontal highway at exactly one specific mile marker. Let's call that marker A. The equation for this road is just x equals a. We can build a road at x equals 2, 1 at x equals -4, and 1 at x equals 10. Every single house on that first road has an exact x-coordinate of 2, no matter how far north or south you travel. It's common to hear x-axis and assume an x equals equation should run horizontally. Just remember, the line cuts through the x-axis. Later on in calculus, these vertical roads act like impassable brick walls. We call them asymptotes. Curving paths can drive right up to them, but they are forced sharply away, unable to cross. Now let's pave some east-west roads. These are perfectly horizontal. Since they only cross the vertical y-axis, their equations are simply y equals a number. Watch as these three lines sweep across the grid. Y equals 2, y equals -3, and way up at y equals 10. Be careful not to mix up the main highways. The horizontal x-axis is actually the line y equals 0, and the vertical y-axis is x equals 0. These horizontal roads have zero steepness, or zero slope. In calculus, you look for this zero slope to calculate the exact peak of a thrown object's path. Perfectly straight north-south and east-west roads give us a foundation, but a functional city requires diagonal roads to connect everything. Mapping a tilted road requires two pieces of information, a starting house and a trajectory. On our grid, that starting house is a coordinate point, and the trajectory is the slope. We combine them into the point-slope form. We can build a road starting at the point 2, 3 with a slope of 4, then one starting at 5, -1 with a slope of 2. Finally, a road beginning at -3, 4 with a downward slope of -1/2. This formula is the standard rise-over-run slope fraction, just reorganized using basic algebra. You are simply multiplying both sides by the bottom of the fraction to turn it into a single line of math. Watch out for negative signs here. Because the formula uses subtraction, plugging in a negative coordinate will flip the sign to a positive. You'll use this exact format in calculus to draw tangent lines, straight paths that graze the edge of a curve at a single point. To connect two specific houses, you first calculate the steepness between them. Once you have that slope, you can use either house as your starting point. We link -1, 4 to 5, 6, then connect 0, 0 out to 2, 4. Finally, connect -2, -2 up to 1, 7. Find the slope first, then pick a point to build the road. Connecting two dots this way helps you calculate an object's average speed. In calculus, you will push these two dots closer and closer together to calculate instantaneous speed at one exact moment. Point-slope form is great when you're standing at a specific house, but city planners who need to see how every road relates to the city center often use a different standard. This is slope-intercept form. Here, B tells us the exact spot where the road crosses the main north-south highway, the y-axis, and M tells us the angle it takes from that crossing point. For y equals 3x plus 2, the road hits the y-axis at 2 and angles sharply up. For -2x plus 5, it hits at 5 and angles down. For 1/2 x minus 4, it crosses at -4 with a gentle upward slope. Think of these crossing points as highway exits, or intercepts. To find where a road exits onto the horizontal x-axis, you set your y value to 0. To find the y-axis exit, you set your x value to 0. Take the road y equals 2x plus 4. If we make x 0, it hits the y-axis at 4. If we make y 0, it hits the x-axis at -2. We can do the same to find the exits for -3x plus 9 and x minus 5. Don't let the letters trip you up. The x-intercept happens when y is 0. In calculus, finding these x-intercepts tells you exactly when a moving object, like a car or a rocket, reaches a complete stop. Because this form highlights the starting point on the axis and the steepness simultaneously, it's often the most efficient way to visualize where a road is heading on your map. Sometimes a map uses a format called the general linear equation, ax plus by plus c equals 0. As long as there are no exponents on the letters, this blueprint will always result in a perfectly straight line. We can translate this into our familiar form. For 3x plus 4y minus 6 equals 0, we shuffle the terms to get y by itself. We can do the same for 2x minus y plus 4 and x plus 5y minus 10 until the slope and intercept are clear. This shuffling process is essential for advanced calculus, where you'll often have to pull specific information out of equations where variables are all tangled together. We have our roads, but how do we find the exact coordinate where two different roads crash into each other? That crossing point is the only location on the map that obeys the rules of both roads at the same time. Since the y value is the same for both roads at that spot, we set the equations equal to each other. For y equals x and y equals negative x plus 4, we solve to find the crash point at 2, 2. We can repeat this for our other pairs of roads to find their unique crossroads. If two roads have the same slope, they are parallel, meaning they never crash. In calculus, finding these crash points is how you define the boundaries to measure the physical area trapped between two curving paths. The rules we use to map these city streets are the same rules used to navigate the most complex shapes in math. Mastery of straight lines gives you the blueprint needed to explore everything that comes next.